Welcome back to the course Networks and Distributed Systems based on the text by Jim Carosa and Keith Ross, Computer Networking, a Top-Down Approach. We are in the network layer and this is lesson 13. In the last lesson we started the discussion of routing and we're going to continue with that. So let's pick up where we left off. In a link state algorithm, the network topology and all link costs are known. That is, they are available as input to the link state algorithm. This is accomplished by having each node broadcast link state packets to all other nodes in the network, with each link state packet containing the identities and cost of its attached links. Let me repeat. This is accomplished by having each node broadcast link state packets to all other nodes in the network, with each link state packet containing the identities and cost of its attached links. This is often accomplished by a link state broadcast algorithm. The result of the node's broadcast is that all nodes have an identical and complete view of the network. Each node can then run the link state algorithm and compute the same set of least cost paths as every other node. The link state routing algorithm we see in this slide is known as Dijkstra's algorithm, named after its inventor. Computer science professors have been talking about Edgar Dijkstra for years and years and years. The thing I think about every time I hear Dr. Dijkstra's name is spaghetti code. Dr. Dijkstra was the one that came up with the observation that a computer program that was not developed according to some sort of modular structure resulted in spaghetti code that went in all directions and was virtually impossible to debug. So that was Edgar Dijkstra. Well, Dr. Dijkstra also created this algorithm. A closely related algorithm is Prim's algorithm. Dijkstra's algorithm computes the least cost path from one node to all other nodes in the network. Dijkstra's algorithm is iterative and has the property that after some number of iterations of the algorithm, the least cost paths are known to that same number of destination nodes. And among the least cost path to all destinations, these paths will have the smallest costs. Let's define the following notation. Now look at your screen and identify the variables as we talk about it. D open paren V, cost of the least cost path from the source node to destination V as of this iteration of the algorithm. Or P open paren V close paren, previous node, neighbor of V, along the current least cost path from the source to V. N, as before, the subset of nodes. V is in N if the least cost path from the source to V is definitely known. As we saw in the previous slide, the global routing algorithm consists of an initialization step followed by a loop. Take a look at the process as it flows. The number of times the loop is executed is equal to the number of nodes in the network. At the end, the algorithm will have calculated the shortest path from source node to every node in the network. When the link state algorithm terminates, we have for each node its predecessor along the least cost path from the source node. For each predecessor, we also have its predecessor, and so in this manner we can construct the entire path from source to all destinations. The forwarding table in a node can then be constructed from this information by storing, for each destination, the next hop node on the least cost path from the source to the destination. This figure in the lower right corner shows the resulting least cost paths and the forwarding table in the example host of the network. Whereas the link state algorithm is an algorithm using global information, meaning that at the end of the process each router knows about every other router, The distance vector algorithm is iterative, asynchronous, and distributed. It is distributed in that each node receives some information from one or more of its directly attached neighbors, performs a calculation, and then distributes the result of its calculation back to its neighbors. It is iterative in that this process continues on until no more information is exchanged between neighbors. In distance vector protocols, each router sends its neighbors a list of all the known networks along with its own distance to each one of these networks. Because in software engineering, a list or an array is also called a vector, the list of networks and distances is sometimes called the vector of networks and distances. Therefore, the name distance vector routing protocol. Let's talk about an important relationship that exists among the cost of the least cost paths. Let dx open paren y close paren be the cost of the least cost path from node x to node y. The least costs are related by the Bellman-Ford equation as shown here, where the min in the equation is taken over all of x's neighbors. The Bellman-Ford equation has significant practical importance. The solution to the Bellman-Ford equation provides the entries in node x's forwarding table. Another important practical contribution of the Bellman-Ford equation is that it suggests the form of the neighbor-to-neighbor communication that will take place in the distance vector algorithm. In the distributed asynchronous algorithm, from time to time, each node sends a copy of its distance vector to each of its neighbors. When a node receives a new distance vector from any of its neighbors, it saves the neighbor's distance vector and uses the Bellman-Ford equation that you see here to update its distance vector as we have already seen. If the node's distance vector has changed as a result of this update step, then it will send its updated distance vector to each of its neighbors, which in turn can update their own distance vectors. If all the nodes continue to exchange their distance vectors in such an asynchronous fashion, each cost estimate converges to the actual cost of the least path from node x to node y. In the distance vector algorithm, a node updates its distance vector estimate when it either sees a cost change in one of its directly attached links or receives a distance vector update from some neighbor. But to update its own forwarding table for a given destination, what the node really needs to know is the next hop router along the shortest path to y. The next hop router is the neighbor that achieves the minimum of the distance vector algorithm. Recall that the link state algorithm is a global algorithm in the sense that it requires each node to first obtain a complete map of the network before running the Dijkstra algorithm. The distance vector algorithm is decentralized and does not use such global information. In fact, the only information a node will have is the cost of the links to its directly attached neighbors and information it receives from these neighbors. Each node waits for an update from any neighbor, calculates the new distance vector when receiving an update, and distributes its new distance vector to its neighbors. The process of receiving updated distance vectors from neighbors, recomputing routing table entries, and informing neighbors of changed costs of the least cost path to a destination continues until no update messages are sent. At this point, since no update messages are sent, no further routing table calculations will occur, and the algorithm will enter an inactive state. That is, all nodes will be performing the wait of the distance vector algorithm. The algorithm remains in the inactive state until a link cost changes. Distance vector-like algorithms are used in many routing protocols in practice, including the Internet's RIP and BGP, ISO IDRP, Novell's IPX, and the original ARPANET. When a node running the distance vector detects a change in the link cost from itself to its neighbor, it updates its distance vector, and if there's a change in the cost of the least cost path, informs its neighbors of its new distance vector. Since distance vector does not have a global view of the network, it is possible that routing loops can occur as updates are being passed back and forth. After passing data back and forth, the only information node Y has is that its direct cost to X is 60, and that Z has last told Y that Z could get to X with a cost of 5. It is detecting a routing loop. A routing loop is like a black hole. A packet destined for X arriving at Y or Z as of one update will bounce back and forth between these two nodes forever or until the forwarding tables are changed. The problem is sometimes referred to as the count to infinity problem. The specific looping scenario just described can be avoided using a technique known as poisoned reverse. The idea is simple. If Z routes through Y to get to destination X, then Z will advertise to Y that its distance to X is infinity. That is, Z will advertise to Y that the link cost is equal to infinity, even though Z knows the link cost is advertised as 5. For example, Z will continue telling this lie to Y as long as it routes to X via Y. Since Y believes that Z has no path to X, Y will never attempt to route to X via Z as long as Z continues to route to X via Y, and lies about doing so. However, poison reverse does not exactly solve the routing loop problem. In the distance vector algorithm, each node talks to only its directly connected neighbors, but it provides its neighbors with least cost estimates from itself to all the nodes that it knows about on the network. In the linked state algorithm, each node talks with all other nodes via broadcast, but it tells them only the cost of its directly connected links. Regarding the issue of message complexity, we have seen that linked state requires each node to know the cost of each link in the network. This requires many messages to be sent. Also, whenever a link cost changes, the new link cost must be sent to all nodes. The distance vector algorithm requires message exchanges only between directly connected neighbors at each iteration. We have seen that the time needed for the algorithm to converge can depend on a lot of factors. When link costs change, the distance vector algorithm will propagate the results of the changed link cost only if the new link cost results in a changed least cost path for one of the nodes attached to that link. As for the speed of convergence, the distance vector algorithm can converge slowly and have routing loops while the algorithm is converging. Distance vector also suffers from that count to infinity problem. What about the issue of robustness? What could happen if a router fails, misbehaves, or is sabotaged? Under link state, a router could broadcast an incorrect cost for one of its attached links, but no others. A node could also corrupt or drop any packets it received as part of the link state broadcast. But a link state node is computing only its own forwarding tables. Other nodes are performing similar calculations for themselves. This means that route calculations are somewhat separated under link state, providing a degree of robustness. Under distant vector, a node can advertise incorrect least cost paths to any of or all of its destinations. In 1997, a malfunctioning router in a small ISP provided national backbone routers with erroneous routing information. This caused other factors to flood the malfunctioning router with traffic and caused a large portion of the internet to become disconnected for up to several hours. More generally, we note that at each iteration, a node's calculation in distance vector is passed on to its neighbors, and then indirectly to its neighbor's neighbor on the next iteration. In this sense, an incorrect node calculation can be diffused through the entire network under distance vector. Well, I believe we have talked link state and distance vector to death, haven't we? I think that's enough. So before we move on to hierarchical routing, why don't we take a break and so that you can go back over this video and get a grip on all the information that you've just got and try to formulate in your mind the differences between link state routing algorithms and distance vector routing algorithms. When you're ready, come on back and we'll move on.